Welcome everyone. My name is Maarten. I'm from Delft, and today I will be talking to you about the work that I've been doing with Peter and my supervisor in the Netherlands, Emir Demirovic. And this work got started because we have a tale of two constraints. I have to focus the right window. Yes, a tale of two constraints in constraint programming. Right, there are two main constraint families that we see in many real-world problems. The first one is a clause, a very basic constraint. If you have three things that can be true or false, in this case A, B, or C, we can pose the constraint that at least one of them must be satisfied. One instance where this is very common, for example, is to encode these types of if this is true, then that must also be true relationships. So in, for example, a nurse rostering problem that might look something like this. If a nurse works one night shift, then their next shift cannot be a night shift, right? Because they may need to have extra rest or whatever else. And throughout the presentation, you'll see me use this V notation here, the logical OR, to indicate this. So this is very common in very many constraint models. We have another constraint type 2, that is also very common, and these are linear inequalities, right? So typically you have some statement in the form of the total cost must not exceed the budget. So you have a bunch of partial costs or a bunch of integers, in this case costs 1 through n, and if you add them up, they may not exceed some certain upper limit. This is, of course, the basis for integer or linear programming, integer linear programming. Many mathematical programming models use this constraint exclusively to formulate their problems. And also in constraint programming solvers or constraint programming models, I should say, they are extremely prevalent. So given that we have those two very popular constraints, you would like to think that a constraint solver can reason about the two of them very well. Because really models use both, right? It's not the case that you have a model that uses exclusively clauses or uses exclusively linear inequalities. They are combined in different ways to express whatever real-world requirements you want to express, right? So in many real-world problems, you have these both clausal relationships and linear relationships that you need to capture. So to combine this reasoning, what current CP solvers do is essentially say, okay, well, we'll take whatever the linear does, and we'll try to express that using clauses. Because what CP solvers do is they want to find a clausal proof, the optimization problem. So let's say they want to prove a lower bound, then they will try to find a clausal proof that you cannot have a better solution than whatever the optimal solution is. So it takes the linear reasoning and it converts that to clauses. And while that works, right, CP solvers are very good at solving particular types of problems, it does have a small downside. And to illustrate that, I have this small example. So we have two variables, x1 and x2, and I've plotted a single constraint here, this diagonal, and to the top right of the diagonal are not solutions, bottom left are the solutions, right? And if we now want to start searching, the solver will start doing whatever it's going to do. And at some point, it will reach a state and it will want to know why one particular point, let's say this point here. So can people on Zoom see my mouse pointer? I hope they can, actually, because I've been using it. Yeah. So it will ask, why is this particular point not a solution, right? This constraint will have triggered some reasoning. It will say, okay, that's not a solution. And now the solver wants to know why. And it has to explain this with a clause over x1 and x2. And it will say something like this. Well, you have this region, and in that region, there are no solutions. Okay, the solver says, fine, that's a clause. Great, I can use that. But actually, I now also want to know why this one is not a solution. Okay, then I go to the same constraint again. It gives me, well, because this other region also has no solutions. And you can see where this is going because it may also ask this for this other point, and it will have to then give you yet another clause to block out those additional solutions. Now, in this example, of course, this is quite small. Typically, you have much larger domains. You have multiple dimensions. So the number of clauses you may need can be quite a lot bigger than these three. On the other hand, the solver may not need all of them, right? So it could very well be that the search is magically very good and it only needs one. And then you don't really have a problem, but typically you will need a few to get to for one constraint. So this process really potentially introduces a ton of clauses that your solver needs to reason over. And given that linear inequalities are so prevalent, essentially our goal was to how can we incorporate these linear inequalities directly? How can we reason over them efficiently, saying, okay, this is the one constraint that we care about, and now you take that and run with it. So to do that, we introduced the Hypercube linear constraint, and I'll show you briefly what that looks like. We have essentially an implication, right? So we have a linear constraint on the right-hand side, and then we have some condition that must be satisfied for the linear to fire. Now, this condition is what we call this a hypercube, which is a bit of a misnomer now, but at least originally the hypercube consisted of a conjunction of bounds on integers. So it would be x greater equal some value, y less than equal to some value. Since then, we have also expanded this to include not equals and equality, just so that every clause that a CP solver could generate can actually fit into this hypercube. But we'll stick with the name for now. Yeah, so we have the hypercube, and this is the condition that must be satisfied. And when it's satisfied, you essentially have a regular linear inequality that fires after that, right? So this is, you can think of this if you're familiar with indicator constraints from or integer programming, linear programming. This is essentially an indicator constraint, except though your premise is much more general than just 1, 0, 1 integer. You can have a conjunction of bounds over potentially many integers. And one very nice thing that we will exploit later on as well is that if you have variables with bounds in your hypercube, then those variables can also have non-zero weights in the linear. So there is an interaction between the variables in your linear relationship and the conditionality of when that linear relationship holds. And we'll see an example of that later. So now we'll quickly show how the solver can reason about such a constraint in isolation. Right? And I gave an example hypercube linear here that does not mean anything in particular, but it essentially says, as long as x is greater or equal to 2, you have the linear relationship between y and 2z, and they must not exceed 5. There are 3 propagation rules that we defined, and there are 2 ones that are extremely obvious. The first one is, well, if the condition is true, then you will reason over the linear inequality as if it were always there, right? And even if you don't really know what that reasoning is, I hope that I can convince you that since solvers have been reasoning over linears, they can also reason over linears and sort of turn them off and on. It's essentially the mechanism we've now introduced. Right? The other case that we can identify is that, well, perhaps we can see that we could never satisfy the linear inequality. We're now in some state, and no matter how hard we try, we will never be able to satisfy this linear. So that means the condition must be false. Right? So we set the condition to false. And this is exactly the reasoning that if you put an indicator constraint into existing CP solver, you would get this. Right? There's nothing particularly new and exciting about this. However, like I said, variables may appear in both hypercube and the linear as well. And now we can do some reasoning that you previously could not do. In particular, so I've written this very trivial constraint that looks a bit silly, perhaps, but you could think of this as part of a more complicated constraint that in the current state simplifies to this. And here we can deduce something about x, right? Because if we do case reasoning, we can say that, well, if x is greater or equal to 2, then, of course, the linear must hold. So we have an upper bound on x, 5. But if x is not greater or equal to 2, right, so that thing is false, then that means that x is at most 1, which also means that x is at most 5. So in both cases, x is at most 5. So we will conclude that x is at most 5. And this is reasoning that if you were to decompose this constraint into a clause, and then you have an indicator constraint for the linear, you would not be able to see this, this consequence. And the other nice thing, this is not just a sort of theoretical nicety of this thing. In the implementation that we have of this system, this actually happens quite a lot, which caused many problems. But yeah, this actually triggers quite often, so it seems to be very useful, at least in the problems that we solved so far. So now we've reasoned about an individual constraint, but the true power comes really from being able to combine them. So you have two hypercube linear constraints, and I now want to be able to systematically derive a third hypercube linear constraint that is implied by the conjunction of my premises. And we call this system hypercube linear resolution. And this is a new proof system that is sound. So we've proven that you cannot derive an untrue statement, which is very nice for a proof system. It's complete. You can actually prove any true statement with this. The system exploits both clausal reasoning and linear arithmetic reasoning over the linear components. And it nicely subsumes the resolution proofs that are prevalent in current day CP solvers like our tools. So I want to sketch two rules that we use in the system. I hope that I can do a good job. If not, then after this, we will go back to a practical, like a real world example. So if I lose some of you now, I hope to get you back after a few slides again. So the first rule that I want to show you is what we call weakening. So what we see here is a linear inequality in the 2D space, and it's the equality 2x1 plus x2 equals 6. Okay. Should be less than equal, but that's okay. Now, let's assume for a moment we are really just interested in the region that is x1 greater or equal to 2. All right. In that region, any line that is above what we had before would also be valid. So we can weaken our original constraint by adding a bound to the hypercube, and we can then reduce the coefficient of the variable for which we added a bound. In this case, because everything is positive, that would work. So this allows us to essentially move integer terms in the linear inequality to the hypercube into our discrete disjunctive view of the world. And this rule is very critical to getting the rest to work, which you will see later on. And just to state this a bit more formally, right? So you have, this is the general shape of our constraint. And if we then use the inference rule notation, we can say that if we add this bound to the hypercube, we can essentially add that linear inequality. So that would be minus xj less than or equal to minus d. If we add that to the linear, we lose one of the weight of xj, and we subtract d from the right-hand side. So this allows you to essentially extend, okay, I can introduce arbitrary implied constraints from my original premise, that is h implies this linear. The next rule that is very important for us is to actually deal with this disjunctive nature, right? It's the proposition, oh, right. One thing I should say is that if you apply this rule multiple times, then you can essentially reduce every weight to 0. right? So you can completely obliterate any linear relationship regarding this integer and just only reason about them as disjunctions, at which point you would get what the original example would give you, right? So you will get all of these different clauses, those different regions. Okay, well, this is this axis aligned region that there's no solution. This is the next one. This is the next one. We can also do reasoning by cases over two hypercube linears, right? So let's say we're in this situation here where you have two linear inequalities, R2 and R1, and they have some different part of the hypercube here, but they share this bound, or I would say opposite bounds on X. And those bounds are such that if you take their combination, you have all possible integers, right? So in the number line here, you'll see that all the values are essentially shaded. Which means that for every branch of X, right, whatever value you assign to X, either R1 holds or R2 holds. Which gives us this monstrosity of an inference rule, but it's not so hard once you break it down a little bit. So on the top, first we have our constraint number one, right? Premise number one and premise number two. These are hypercube linear constraints. And now we're saying, well, for whatever value of X, the consequence would be that the conjunction of the rest of those hypercubes implies the disjunction of the two linear inequalities. Now, those of you who are very astute will know that this disjunction is not actually a linear inequality. So this is not a hypercube linear constraint. So we have to somehow find a way to reshape it into one. And for that, we use weakening. So what we do with weakening is we can rewrite either one of those R1 and R2 two clauses. So we can essentially convert them to 0 less than or equal -1, which means that this term is essentially R1 or false. So obviously then we conclude R1. And this is actually the method that we did for the CP-AIOR submission. And it works relatively well. And the other way that you could do this is to use weakening to move towards the situation where one linear essentially implies the other, right? So you have the terms are have all the same coefficients, but your bound is weaker on the right-hand side. And if you can do that, you can take the weakest of the two, and you would have the same disjunction. So that essentially allows you to collapse this disjunction into one linear at the cost of introducing some additional new bounds into your final hypercube. And during my stay here, one of the things that I'm trying to figure out is which one of these two is better. Because theoretically, there's no clear, like they are incomparable in terms of strength. So this is purely an empirical question, right? Okay. So that was most of the very difficult math that I wanted to show you guys. So those of you who checked out, I hope that I can now get you back in to show you why this is a very cool idea in a more real world example, right? Which is still a toy for the presentation, of course, but nonetheless. And the example that I want to discuss with you is bin packing. So we want to pack parcels into containers, bins. And one key thing that I would like to do for this example is to say that, well, my parcels have configurable size. So depending on how you pack them in containers, you can give them a small, a medium, or a large box to put them in, for example. And you have to decide this for every parcel. So we have a container, it has a capacity, and then we have two parcels with a weight. So for parcel 1, it can be weight 3, 4, 5. And for parcel 2, it can have weight 4, 5, 6. And now let's, for sake of argument, assume that we are in a state, which is what I've graphed or shown here as well. The solver has put both of them in container 1 in the current subtree, right? So their total weight combined cannot exceed 8. Now, if you put this into a CP solver and you write a propagator for it, it will discover this fact, right? Given that W1 plus W2 cannot exceed 8, so the weight of two partials cannot exceed 8, and the weight of partial 2 is at least 4, we must conclude that the weight of partial 1 cannot exceed 4, right? And therefore the value 5 does not work for W1. So this will happen in any CP solver. Now, the question is, how do you explain this reasoning to put into that proof, right? So that's what we're going to look at now. How do you explain the propagation W1 does not equal 5 in the proof, which for your standard CP solvers are clausal proofs. So you would get something like this. It says, well, if I have assigned both parcel 1 and parcel 2 to container 1, which are these x1 and x2 variables, and I have a weight of parcel 2 that is at least 4, then the weight of parcel 1 cannot exceed. Right? This is what would go into a causal proof in, for example, all our tools. But our HL would allow us to say something like this. Well, if they are both in this container, parcel 1 and parcel 2 are in container 1, then the addition of their weights cannot exceed 8. The sum of their weights cannot exceed 8. Now, why is this nice? So let's say we're now in a state where we have somehow concluded or decided that parcel 2 should have weight or will have at least weight 5. Right? The clause does not apply anymore because whilst x1 is still 1 and x2 is still 2, W2 is not at least 4, it's at least 5. So we have to now introduce a new clause for our additional reasoning. However, for the HL, it's not true, right? This is still satisfied because nothing has changed, and I simply have a new propagation in our linear relationship. So this is really where you can see how you get additional strength from these constraints if you can introduce them. So that's what I wanted to talk to you with today. I'll briefly summarize what we've seen. So I've introduced you to the Hypercube linear constraint. This is a constraint that combines clauses and linear inequalities into one formalism. I've quickly shown you how we reason about individual constraints, how CP solvers would propagate based on these constraints, and shown you that taking this conjunctive view actually allows you to do stronger propagation than doing a decomposition of the constraint. I've touched upon parts of the proof system. For those of you who are very interested, everything is in a paper at CP AIOR this year with all the proofs and all the nice maths. And we also saw like a more real-world example of why this could be exploited in real-world problems in CP solvers. So where do we go into the future? So open directions are obviously we would like to see further integration with constraint programming propagators. I gave you one example here. There are possibly many more. You could think about ordering constraints where you know that if I want one thing to be before another variable, like I want one variable to be less than another variable, then you have already this immediate arithmetic relationship between the two, where clauses would have to introduce a new clause for every shift that you do of one of those two variables. You could think about how stuff like automatic search and many other solver heuristics are impacted by this, right? Because essentially, many of the heuristics are designed around these clausal proofs, right? Where do we search in the space is all guided by what parts are hard, where can we find many clauses, where do we find many conflicts. So that will have to be tuned at the very least, if not redone. Similarly, in the experiments that we have done so far, one of the big problems is that we at some point learn quite a lot of them, which means it becomes very expensive to reason over all of those. And this is a well-known problem in stat solvers because they essentially throw out half of them every now and then, or some fraction of them every now and then, to make sure that this does not become a problem. So there are a bunch of sort of these practical things that you would still need to do to get a very good implementation of this. And yeah, so that was the talk. If you're interested, this is the citation. I hope it will go out next week at CPIR. I will quickly plug the CP solver that I'm also working on. For those of you who are interested in talking to me about that, also very welcome.